All right. Your next homework assignment is due on Wednesday, and I've got a couple of hints for you on that. The first, I believe one of those problems is taken from the textbook, problem 1222, and we previously talked about flow per unit width. So, for example, if you have a rectangular channel and you know the flow rate and it has some width, then the flow per unit width, lowercase q, is the flow rate divided by the width of the channel. So flow per unit width, we've talked about it before. Another way to determine the flow per unit width is the velocity times the flow depth. So v times y also will give you the flow per unit width. Because think about what are the units of flow per unit width. It's meters squared per second. That's the units of flow per width. So this is going to give you, the velocity would be meters per second, and the depth is meters. So you also get meters squared per second from velocity times depth. So you'll have those things in problem 1222. And then the other aspect of this hint is just that you can determine the flow regime, meaning subcritical versus supercritical. One way to do that is with the Froude number, but here I think it'll be simplest just to compare the given flow depth to the critical depth. And remember that you can determine the critical depth for a rectangular channel as flow per unit squared divided by g to the 1/3 power. So that's just going to be flow per unit width divided by g to the 1/3 power. That's a simple way to determine the flow regime, whether you've got supercritical or subcritical flow, is just if the depth y that's given is more than the critical depth, that tells you you've got subcritical conditions. If the given flow depth y is less than the critical depth, then you've got supercritical conditions. All right, so that's due by Wednesday at 1 o'clock. Then the other thing that's on your plate right now is the project. Over the break, I graded all of the demand estimations. I provided pretty extensive feedback, the written comments. And so please review and update your estimates based on the comments that I've given you. I'll be spending the extra time when I grade your final report to see whether you fixed the issues that I identified. And the fastest way to a low grade on the project is to just go with the same mistakes that you've made the first time around. The reason why we do these draft submissions is partly to break it up into smaller pieces and make it more manageable, but then it's also so that your finished product is going to avoid some of the mistakes that you made earlier on. So I can catch a mistake, tell you about it, you can make the fix, and then the final version of your project is really well founded. So please update your demand estimation, but really what phase 2 is all about is the pipe sizing. And so what you're going to do for that is you're going to prepare PDF files and upload a PDF file showing your network and the annotations, which includes like pressure, diameter. All the annotations you need are mentioned in the handout, but you're just going to upload two things: a PDF file of the network under the demand, meaning the peak flow rate, and then the static conditions, how your pipe network is doing. So that's by Friday at 1. Any questions about the announcements? One more hint on the homework. This is for problem 25. So you have an expansion in this problem, and it's asking you in the problem to find out the new flow depth downstream. So initially there was one flow depth, there's going to be a new flow depth when the channel gets wider, and the given conditions was that we knew the depth was 4 feet, the velocity was known, so everything you'd need to calculate the specific energy at 1 is given. And they also mentioned that there's an expansion coefficient, that you're losing some energy as the channel expands. So the way that you would apply that to the specific energy equation is The amount of energy at 1 is going to be the depth and the velocity head. So you have all of the given information you need to find out the specific energy at 1, because the depth is 4 feet, the velocity is known. So here you can find the total E, specific energy at 1, and then all of that energy at 1, part of it goes to the expansion. So that's what this last term in the right-hand side of the equation is. C times the velocity head. And you probably haven't seen the velocity head expressed this way before. We've seen the velocity head expressed as v squared divided by 2g. So v squared divided by 2g, that's velocity head. What's another way that you've seen the velocity head expressed in the past?
Q squared over 2g a squared.
Did you say q squared divided by 2g a squared?
Yeah.
Yep, that's another one. And so here's another one. Flow per unit width, so lowercase q squared divided by 2g y squared. So this is another way to know the velocity head. And the reason why it can be useful is that we know the width of the channel here at location 2. We know the width is 10 feet. And we know the flow rate, big Q. And so we can find the flow per unit width. But we don't know the depth. So the depth is going to be an unknown, and that's what you're solving for. What is the new depth downstream? So the new depth is going to be the depth, the velocity head, which is a function of the depth, and then the energy loss, which is some coefficient multiplied by the velocity head. So here C is 0.5, and so basically what you've got is 1.5 times the velocity head. So this is going to be a cubic equation, and we've had several example problems in the weeks before spring break where you were getting some refreshed practice on solving for the roots of a cubic equation. And so there's going to be a negative root, which you throw out, and then there's going to be a small value for the depth, which is the supercritical root, and then there's going to be the larger flow depth at 2, which is the subcritical root, and then you know which of those to choose based on whether the initial upstream flow conditions were supercritical or subcritical. So what you could do is you can find out at 1 is y1 greater than yc. That's one way to diagnose the flow regime. The other would be calculate the Froude number at 1. And either one, you're welcome to do either one. But I just wanted to show you how to handle an expansion. An expansion is similar to a local loss. When we were talking about pipe flow, there's these locations where energy is lost at a point. And an expansion like this is similar in the way that we handle it from an energy perspective. All right, so any questions about that hint? All right. Now, just as a review, in the class meetings before spring break, we were talking about when there's a step down or a step up. And what we used was a specific energy analysis to find out the new flow depth after a step down or a step up. So specific energy is the depth of flow plus the velocity head. So E, specific energy, is the depth of flow plus the velocity head. V squared divided by 2g, or we could say Q squared divided by 2g a squared, or we could say lowercase q squared divided by 2g y squared. So that's specific energy. And the energy at 1 is equal to the energy at 2, but in the case of a step down, you're gaining energy between 1 and 2. So E2 is the energy that you had at 1 plus the step down. But if it's a step up, there's going to be less specific energy at 2 because of that vertical elevation gain. And so E2 is E1 minus the delta Z. Just to refresh your memory of whether you're adding or subtracting the delta Z when you're going from 1 to 2 in the downstream direction. Okay, so what we went through was this process of solving for y2 at the downstream location and solving a cubic equation. If there's a relatively small step, a delta z that's small, then it's going to cause a relatively minor change in the elevation. So the y2 is going to decrease, is what we learned, if it's subcritical flow. And we looked at the specific energy diagram to predict how that would occur. Just to refresh your memory of what the specific energy diagram looked like, it's this one. So if we had some initial flow depth and we're in the subcritical range, then the step down meant that we were going, that the delta z step up meant that we lost energy, so we're shifting to the left, and it was going to be less elevation at the downstream location 2. So back to this, the small step causes a small reduction in y, but if it's a little bit larger step, it reduces the depth a bit further. And there was a question asked, what happens if you have a really big delta z? There is some critical limit that can't be exceeded without causing a choke to the flow. So the delta z that causes you to have critical flow at 2 is the maximum step that can be accommodated without causing y1 to get deeper. So you can see here that what we have is the critical depth because we've got some delta z, and initially we had subcritical conditions, but we were getting the flow depth at 2 getting shallower and shallower, and so it's approaching that critical depth. And the critical depth, remember, is the depth that is the most efficient in terms of conveying the flow rate with the least amount of specific energy. But if you have a delta z that exceeds that critical step height, then what happens is there's going to be a new flow depth upstream at location 1. So instead of E1, we now have E prime 1, with the prime meaning like the new depth that will arise after choking has occurred. So if delta z is big enough, what it does is it causes the water upstream to pool until there's enough energy to cause critical flow over this new obstruction. So at the critical flow condition, the flow depth is 2/3 of the specific energy, and the velocity head is 1/3 of the specific energy. And for a rectangular channel, what that means is that we can calculate the specific energy when conditions are critical by just multiplying the critical depth by 3/2, and then that'll give you the overall specific energy. Okay, so just again, to look at the specific energy diagram, initially the water was flowing with E1, the specific energy at location 1, but then that delta z, the first one that was a relatively small step, since the flow conditions were subcritical, that meant that the depth decreased a little bit, and when we had a larger delta z, the vertical step upwards, it decreased the height a bit more. But there's some step height that's as far down as you can go. So this delta z sub c, the critical step height, where you can't go any further to the left because it's off the specific energy diagram. So from E1 over here to the minimum specific energy is the largest step height that can be tolerated. And if you go further to the left, then you just need a new specific energy diagram. So a step larger than the critical step means that there's not enough energy to push the water over the obstacle. So in the initial case here, there is enough specific energy to get the water up over this small delta z. And there's enough energy to get the water over this obstruction. And this one, there's just barely enough. Location 1 has just barely enough specific energy to get over this obstruction. And the way that we know that it's just barely is that it's flowing at the critical depth here at the obstruction. And so it's flowing at its most efficient depth. And then if the height is any larger than that, then it's going to cause this pooling. And by pooling, what I mean is that the water is getting deeper at the upstream location 1. So there wasn't enough energy before pooling to push the water over the obstruction, but the water will back up. It's just temporarily the in and the out won't be equal. That the water will accumulate upstream of the obstruction until the water depth is high enough, and then it has enough specific energy to get over that new obstruction height. So remember, here's the specific energy diagram, and anytime you've got a delta Z that's larger than the critical depth distance over to your original energy upstream distance, then that's what's going to cause pooling. Okay, so let's go through an example calculation where we calculate the maximum step height that could be tolerated. So here's the scenario. We have a rectangular channel, and upstream we know that the flow conditions are such that the depth is 0.9 meters and the width of the channel is 2.5 meters. So water's flowing downhill, and here at location 1, the Y1 is 0.9 meters. That's our flow depth. And the flow rate is 4.25 cubic meters per second. Now, from this flow rate, we can calculate the velocity at 1. So V1 is going to be Q divided by A1. So it's going to be Q, which is 4.25 cubic meters per second, divided by our cross-sectional area, which is 2.5 meters by 0.9 meters. Okay, so we can calculate the velocity at 1 and find the energy at 1. Now at location 2, so downstream, there is a step. So there's this step, and for part A, let's just find out if the step was 0.05, then what would be the new flow depth that occurs here at 1. So we want to find out what is Y2 over that obstruction, where it's 0.05 meters. So this first part A, is a bit of a review, because what we're going to do is we're going to find the velocity at 1, find the Froude number at 1 to diagnose the flow regime. We got to know if we're supercritical or subcritical. Find the energy at 1, it's the depth plus the velocity head. And then we can find Y2, because remember that Y2, let me write this part, for a step up like we've got, E1 minus delta Z is equal to E2, because the step up is robbing energy that otherwise would exist at location 2. Okay, so let me pause for a second, give you a chance to calculate these things. Find V1, the Froude number at 1, the energy at 1, and then the new flow depth at location 2 for part A. And then together we'll go through the process of calculating the delta Z max that can be tolerated. Okay, let me just show you where all of this is heading. The key thing, remember, is that we are comparing the specific energy at 1 and the specific energy at 2, and we know that we're going to be losing some of the energy in the transition because of the step up. So the first thing that I did was calculated the velocity at location 1, which we can get because we know the width of the channel is 2.5, the depth of the flow is 0.9 meters, and so we've got the velocity at 1 is 1.889 meters per second. And the specific energy that there is going to be at 1 is because of the depth and the velocity head. And then if we subtract out the delta Z, then that'll give us the specific energy at 2. So you can see here, I've said let's add together the flow depth of 0.9 meters, which is the upstream flow depth here at location 1. the velocity head at 1, and then subtract out 0.05 meters. And so what that leaves us with is the specific energy at 2 is 1.0319 meters. So that's going to be distributed in two places. Part of that energy is in the depth, and part of that energy is in the velocity head. And now I'm writing the velocity head not in terms of v, but I want to write the velocity head in terms of the unknown depth, y, because it's going to be in two places. You know, the velocity head changes as the depth changes. So that's why I have to, instead of writing v2 divided by 2g, v2 squared divided by 2g, the velocity at location 2 changes as the depth at 2 changes. So that's why here I'm writing the velocity head in terms of y2. So you can see on the left-hand side, I'm starting to set this up as the cubic equation. On the left-hand side is the energy at 2, and then the right-hand side is the depth of flow, and then the velocity head as a function of the flow depth. And then multiply each term by y2 squared. And so we've got y2 cubed minus 1.0319 y2 squared plus 0.1473. So it gives us a couple of different roots. It gives us the negative root, which we can reject. It gives us this small flow depth, which is the supercritical root. And then it gives us the larger flow depth, which is the subcritical root. And to know which one of these flow depths we're going to get downstream, we have to know upstream what was the flow regime before the step occurred. We have to know here at location 1, were conditions supercritical or were they subcritical? And so you can see that I've calculated the Froude number at location 1. And the Froude number at location 1 was 0.636. And so that means that that's the subcritical root. And so if conditions were subcritical before the step, then they will be subcritical after the step. So when we have this delta z height of 0.05 meters, then the new flow depth is going to be 0.804 meters. Okay, so I'll pause for a moment in case you need to copy some of that down, and then we'll take a look at how do we calculate the maximum step up that can be tolerated. Just to reiterate, what we did was we found out how much specific energy is there at 1, and then we said, where does that energy go? So some of it goes towards getting up over the step, and then the remaining energy is going to be partly in the depth, partly in the velocity head. And so we expressed the velocity head as a function of depth so that we could solve for y2. So that's all we did so far, and of course we knew which of these cubic roots to select based on the flow regime at 1. But now, in part B of this example, it's saying what is the maximum obstruction allowed before there's choking. By choking, what I mean is before the obstruction is so high that it causes the flow at 1 to have to get deeper to accumulate enough energy to get up over the obstruction. So before choking or before pooling, it just means there's going to be a temporary unsteady flow conditions where water accumulates upstream of the obstruction as the flow is gathering enough energy to get over the new obstacle. So what do we know about what's the unique thing about the flow depth when we're at that point where it's at its maximum step up? When you're at the maximum delta z that can be tolerated, what's the flow depth over the obstruction? When you've got the biggest delta z between your initial upstream the biggest delta Z that can be tolerated. We're not yet beyond the specific energy diagram, but we're just at that maximum delta Z. What's the flow depth over the obstruction when you're at that maximum delta Z? Critical conditions. So what we know is that we're going to say, let the flow depth here be critical. So YC. All right. So if we have critical conditions over the obstruction, then that tells us a lot, because we can calculate the Y sub C using the flow per unit width squared divided by G to the 1/3 power. And remember, this is only valid when you have a rectangular channel. We do. If you don't have a rectangular channel, then you have to calculate the critical depth using the full Froude number equation. But for our purposes, this is fine. The flow per unit width, lowercase q, is just going to be the 4.25 cubic meters per second divided by the 2.5 meter width of the channel. So that's 1.7 meters squared per second. Okay, so over here, we're calculating the flow per unit width. It is 1.7 meters squared per second. Square that, divide by 9.81 meters per second squared, and take all of that to the 1/3 power. Okay, so the critical depth is 0.665 meters. So when the delta Z is just as high as it possibly can be, it induces critical flow over the obstruction. Here is the critical flow. We know that that would be the depth when that happens. And then for that depth, we can find out what the velocity is going to be. So if you got just to show like the cross-sectional view, the depth is 0.665, and then the width of the channel was 2.5 meters wide. Okay, so the velocity at location 2 is the flow rate divided by the area. 2.5 meters by 0.665 meters. So the flow rate was 4.25 cubic meters per second. So the velocity at location 2 is going to be 2.55 meters per second. So the specific energy equation says that the energy at 1 is equal to the energy at 2 plus the obstruction. Or the way it was expressed here was minus the delta Z if it's on the left-hand side of the equation. So we've got to step up. So E1 minus delta Z is equal to E2. So E1 minus delta Z is equal to E2. And of course the energy is in what locations? It's the Y1 plus V1 squared divided by 2G minus the delta Z max. And then it's equal to the critical depth that we've just calculated plus V2 squared divided by 2G. And we know the depth at 1, that was a given. The velocity at 1, we know that from before, from the part A, what we got was that the velocity at 1 was 1.889 meters per second. We calculated that in part A. So we know Y1, we know V1, we know YC, we've just calculated that. We know the velocity at 2, so the only unknown is the delta Z max. Okay, so let me show you what those calculations look like. We had calculated the critical depth for this rectangular channel. We know the velocity at 2. We've done that on the board, 2.555 meters per second. So then the energy equation is the amount of energy that there was at 1. Here I've moved the delta Z max over to the other side of the equation. The energy at 2. So the highest that we can go with that delta Z max without causing pooling would be 0.084 meters. And any higher than that, then the water is going to get deeper upstream at location 1 in order to accumulate energy to get over the obstruction. But this is the delta Z max that corresponds to critical flow at 2. So it's the delta Z max that, if we go back to the specific energy diagram, it's the delta Z that would cause critical flow over the obstruction. Any questions so far about how to use specific energy and this idea of the obstruction height that's as high up as you can go? Okay, so choked flow just means that you've achieved that maximum constriction. Either the channel is getting really narrow or there is a really tall obstruction that if you go beyond what's the maximum that's allowed, then the water elevation upstream is going to be affected by that. And the reason why it's significant is that if the water level is getting deeper and deeper to accumulate energy to get over the obstruction, then that could submerge things, hydraulic structures upstream. So let me just go through an illustration. Let's say that we have water flowing with steady, uniform flow. If conditions are steady and uniform, what equation do you use to find the flow depth? We don't have to use the specific energy analysis. We can use something else if conditions are steady and uniform. It's named after a person.
A lot of equations named after people.
Not a lot of open channel flow equations that we've learned this semester. We've got open channel flow. You find the flow depth with what? Manning's equation. That's right. Yeah, so if you've got steady uniform flow, it's easy to find the flow depth just with Manning's equation. But let's say that we put in an obstruction. This looks like a tall one. We just dropped a concrete wall in the river, and the concrete wall is 10 feet tall. And so if the flow depth is 10 feet and so is the wall, obviously the water can't get over that without something changing. So what's going to happen is if you drop an obstruction that's above the delta Z max, and this obviously is. I mean, we haven't done the calculations, but if the obstruction is as deep as the water, then you've gone beyond the delta Z max. So what's going to happen is that the water is going to get deeper than it was originally until there's enough energy at 1 so that it can flow at the critical height over the obstruction. So the water is only going to pool to the minimum height required. It's not going to get any deeper than this minimum specific energy required to get over the obstruction. And the critical depth represents the most efficient flow condition, the flow condition with the least amount of specific energy required. So that's why it flows at the critical depth. It's not going to flow at anything else because it's the least additional energy required to get the water over the obstruction. So sometimes what we want to know is, we know what the original flow depth was before this 10-foot tall brick wall was put into place. Originally it was 10 feet, but we want to know what's going to be the new flow depth after the water's getting over the obstruction. So Y prime 1 just means the new flow depth after choking has occurred. So the way that we do this is we first of all find out how much energy is required to get over the obstacle. So our obstacle is 10 feet, so you need to have at least 10 feet of specific energy, but then you also need enough specific energy at 1 for there to be the critical depth. So the energy required is the minimum specific energy, which is 3/2 of the critical depth, because it's going to be the critical depth plus the velocity head associated with the critical depth. And what you may not remember, I mentioned it in the class meeting on Friday before spring break, is that when flow conditions are critical, the specific energy is 1.5 times the critical depth, because the specific energy is the depth and the velocity head. The velocity head is 1/3 of the specific energy. The critical depth is 2/3 of the specific energy. And so if you've got critical conditions, you can find E minimum by just multiplying 1.5 times the critical depth. Okay, so then our calculation process here is to find out how much energy was there originally at 1. And you find out the available energy and compare it to how much is required. And if there's more energy required than there's available, then choking will occur. And then the new flow depth is going to be whatever is the minimum flow depth that gives you that required energy. All right, so we've got just 6 minutes, and I don't know if that would be enough time for you to actually crunch the numbers yourself. So instead, what I'll do, which is less satisfying but maybe allows us to cover more ground, is I'll just show you the calculations for this example where we've got 500 CFS going through a rectangular channel. So that makes our calculations a little bit easier since it's rectangular. The width of the channel is 10 feet. The depth of flow you can see is 10 feet. And we want to know, how deep does the water have to get over a 10-foot obstruction? Any guesses? How deep do you think it's going to have to get? Right now it's 10 feet. What do you think, 11, 12, 1,000? Probably not 1,000, right? That seems too deep. It's going to be enough so that there's the specific energy at 1 that can achieve the delta Z and 3/2 times the critical depth. Okay, so let me show you these calculations, how we can find out what is the new depth after choking occurs. So what we do is we find out the critical depth based on the fact that the flow per unit width, 500 cubic feet per second, and it's a 10-foot wide channel, so it's 50 feet squared per second is the flow per unit width. Square that, divide by G. We're in traditional units, and so G is 32.2. So the critical depth is 4.265 feet. And the minimum specific energy that's required is going to be 3/2 that critical depth. So 6.398. And the total energy to get over the obstruction is going to be the 10-foot delta Z plus this minimum specific energy. So we have to have enough specific energy so that we've got 16.398 feet at 2. And we look at how much energy was there originally before we put that choke into place. Well, if we add together the depth and the velocity head, and here, I guess I could have done the velocity head as v squared divided by 2g. I don't know why I had to do it this fancy way. I guess maybe just to get some practice with flow per unit width squared divided by 2g y squared. So there was only 10.388 feet of energy at 1. So let's look at the picture again. There's 10.388 feet here at 1. And we need to have 16 feet of energy to get over that obstruction, which we don't have. 10 is less than 16. So what that means is that the water depth at 1 is going to get deeper. Y prime 1 is going to continue to get deeper and deeper until it's deep enough to cause that minimum specific energy at 2. So the logic here is that the E required is greater than the E available. So this sill, which is just another word for like a blockage or a vertical obstruction, that's causing the choked flow. So the new upstream depth is going to be, you set the required energy, 16.398 feet, and multiply it by the velocity head and the velocity head and the depth. I guess this is maybe now why it would be useful for us to write the velocity head in terms of flow per unit width, is because the flow per unit width stays the same and it's a function of the unknown depth. So y prime 1 means the new depth after the depth has gotten deeper and deeper after choking. Okay, so 16.398 feet is equal to the unknown depth, and we got the flow per unit width squared divided by 2g depth y1 prime squared. Cubic equation, and it's the larger of these two positive roots because it's going to be flowing at subcritical conditions at 1. Because y1 is greater than the critical depth originally, then it's going to be subcritical after the pooling. It's getting deeper, even more subcritical than it was originally. So what that means basically is that the new flow depth is going to be 16.25 feet. So it started at 10 feet and has to get deeper because that's how energy accumulates. You get enough energy to get over the obstruction by allowing the water to get deeper and deeper. So now energy available equals energy required after the pooling. All right, that's it for today. Remember that the two things that you've got on your plate is this homework assignment due Wednesday, and then the pipe optimization for phase 2 of the project on Friday.